When the temperature drops to -40 and the wind is moving so fast the snow goes horizontal.
The men who built wrong find out immediately. The fire drops at 3 a.m. The breath clouds inside their own home. The propane bill arrives and grown men go quiet looking at it. That is not a worst-case scenario in Alaska. That is a Tuesday. And for decades, tens of thousands of people have been accepting that reality as normal. Not because it is acceptable, because they did not know there was a better answer.
But something is changing, quietly, one build at a time, on remote lots and off-grid properties across the state. Smart Alaskans are walking away from traditional cabins, not because they ran out of money, not because they hate what their fathers built, because they found something faster to build, cheaper to heat, and structurally superior in every condition Alaska can throw at a structure. Something that laughs at permafrost, sheds snow loads that would fold a standard roof, and locks heat inside so efficiently that the men living in them are cutting their fuel bills in half and sleeping straight through blizzards that used to own them. Most people have never seriously looked at it. That is about to change. Hit subscribe now, because by the end of this, you will understand exactly why the Quonset hut is the most underrated cold weather structure ever built, and why the men choosing it are living better than anyone still fighting a traditional cabin every single winter. If you have never lived in Alaska or anywhere with genuinely brutal winters, you might not understand how completely a traditional cabin can work against you. Not just inconvenience you, work against you, actively, structurally, every single season. Start with the roof. A standard gable roof is two flat planes meeting at a peak. It looks right. It looks like a cabin is supposed to look. But in a real Alaskan winter, those flat planes become a liability the moment snow starts falling. Snow lands and it stays. It does not slide. It builds and builds and builds until you're dealing with hundreds of pounds, sometimes thousands of pounds, of dead weight pressing straight down on your structure. The trusses were not designed for that. The walls were not designed for that. And every year, across the state, structures that looked perfectly solid in September are groaning under loads they were never meant to carry by February. Then comes the ice. Ice dams form at the eaves when heat escapes through your roof deck, melts the snow at the peak, and that meltwater runs down toward the cold eaves and refreezes. The water backs up under your shingles. It finds every seam, every nail hole, every gap where two materials meet. Then it freezes. Then it expands. Then it destroys. Slowly, invisibly, relentlessly. You do not see the damage until the ceiling stains, until the wall starts weeping, until the rot has already taken hold inside the structure you cannot see. And then there is the heating. A rectangular cabin is essentially a box engineered to lose heat from every possible surface. Cold air infiltrates at the foundation. It sneaks through wall penetrations. Heat rises through the attic because a square building gives it every opportunity to climb straight out the top. You burn through propane at a rate that makes the bill feel personal. You stack firewood all summer long just to survive. And even then, even after all of that, you wake up at 3 a.m., the fire has dropped, and you can see your breath inside your own home. That is the life tens of thousands of Alaskans have been accepting as normal. Not because it is acceptable, because they did not know there was a better way. The Quonset hut has been sitting in plain sight since 1941. The United States military needed a structure that could solve an almost impossible problem. It had to ship flat. It had to be assembled fast by soldiers with no construction experience, no specialized tools, no heavy equipment. And it had to survive every climate on Earth, from the heat and humidity of the South Pacific to the brutal cold of the Arctic. The engineers at Quonset Point Naval Air Station in Rhode Island solved that problem with a half-cylinder, a steel arch, no corners, no flat roof planes, just one continuous curved surface that starts at the ground, sweeps overhead, and comes back down the other side. Simple, elegant, structurally brilliant. The military built over 150,000 of them during World War II. They went up in hours. Soldiers slept in them in the Pacific. Mechanics worked in them in Iceland. They housed field hospitals, mess halls, and command centers on every front of the war. And they survived. Conditions that destroyed conventional structures left Quonset huts standing. When the war ended, the design did not disappear. It evolved. And here is where most people carry a misconception that stops them from ever seriously looking at this structure. Today's Quonset hut is not a corrugated metal shed with a dirt floor and a leaking seam running down the middle. That image is decades out of date. Modern Quonset structures use galvanized steel arches, pre-engineered and pre-punched, that ship flat on a standard flatbed truck and bolt together on site without a crane, without heavy equipment, and without a crew of 20 specialists. The design that kept soldiers alive in Iceland is now keeping Alaskans warm, and it is more refined, more efficient, and more livable than most people ever imagined before they actually look at one. Now look at the snow problem again, because this is where the arch earns everything. A curved roof does not hold snow the way a flat plane does. Physics takes over the moment the storm starts. The arch redirects the structural load downward and outward through the curve, and snow hitting that curved surface does not accumulate the way it does on a flat plane. It slides. The arch under compression is one of the most powerful load-bearing geometries in all of engineering, and has been proven for a very long time. The Romans understood this when they built their aqueducts 2,000 years ago. The same principles that kept Roman stonework standing for millennia are what make a properly engineered Quonset arch handle snow loads that would fold a conventional truss roof. In a place where snowfall is measured in feet, not inches, that is not a secondary advantage. That is the difference between a structure that survives Alaska and one that merely endures it until it cannot anymore. A properly designed Quonset arch can carry loads that would collapse conventional framing, and it does it through geometry rather than brute material mass. Less weight in the structure itself. More capacity to handle what the environment throws at it. That combination does not happen by accident. It is what the arch was designed to do. And unlike a gable roof where you are constantly managing the snow load, shoveling, monitoring, worrying, the Quonset arch handles it passively. You do not have to climb up there at midnight in a storm. The structure does the work. You stay inside and stay warm. Ice dams are one of the most destructive recurring problems in cold climate construction, and most people who live with them have simply accepted them as part of the annual cycle. They should not, because the conditions that create ice dams are specific, and a properly built Quonset eliminates both of them. Ice dams require two things: a temperature differential across the roof surface, where the peak is warm enough to melt snow and the eaves are cold enough to refreeze it, and a low slope or flat surface where that meltwater can travel slowly enough to freeze before it runs clear of the structure. A traditional gable roof with inadequate insulation creates both of those conditions naturally. Heat escapes through the roof deck unevenly. The eaves stay cold, water backs up, and the destruction begins. A properly insulated Quonset arch eliminates the temperature differential. The continuous curved surface, when insulated correctly from the interior, maintains a consistent thermal profile from peak to base. There is no warm zone at the top and cold zone at the eaves, because the insulation is continuous and uniform, and the geometry of the curve means that any water that does form on the exterior surface moves immediately. There is nowhere for it to pool, nowhere for it to slow down and refreeze into a dam. The ice dam problem does not become a smaller problem on a Quonset. It essentially disappears. For men who have spent years fighting ice dams on traditional cabins, pulling off damaged shingles, replacing rotted fascia boards, dealing with interior water damage every spring, that single advantage alone is worth serious attention. This is where most people ask the obvious question, and it is a fair one. How do you insulate a curved metal surface? Metal conducts cold. Steel in an Alaskan winter without proper insulation is not a building material. It is a radiator running in reverse, pulling heat out of your living space as fast as you can generate it. So how does the Quonset solve what seems like a fundamental problem? Closed-cell spray foam. And it works better on a Quonset than on almost any other structure you can build. Closed-cell spray foam adheres directly to the interior steel surface. It fills every gap, every seam, every potential cold spot without exception. It creates a continuous thermal and vapor barrier across the entire interior surface of the arch, and adds structural rigidity to the steel at the same time. There are no stud bays where insulation settles and leaves cold spots over time. There are no corners where bats sag away from the surface and create thermal bridges. There are no penetrations that compromise the envelope. You spray the interior of the arch, and you have created one of the most airtight, thermally efficient building envelopes possible in cold climate construction. But here's the part that changes a heating equation completely. The interior volume of a Quonset is fundamentally different from a rectangular cabin of the same footprint. In a rectangular cabin, you are heating a cube. Every cubic foot of air from floor to ceiling, wall to wall, has to be brought up to temperature and kept there. In a Quonset, the walls curve inward as they rise. Livable space concentrates at the center and near the floor, exactly where you and your wood stove and your dog actually exist. The dead air volume up in the peak of the arch acts as a natural thermal buffer. You are not burning fuel to heat space you will never occupy. The numbers that come out of this combination are real. A well-insulated Quonset hut can cut heating costs by 30 to 50% compared to a traditional cabin of similar floor area. That is not a marketing figure from a kit manufacturer. That is a lived experience of the men who have made the switch and are now burning half the firewood and spending a fraction on propane compared to what they were hemorrhaging in their old rectangular boxes. If you have never dealt with permafrost, it is easy to think of it as just cold ground. It is not. Permafrost is one of the most unpredictable, unforgiving building conditions on Earth, and it sits beneath enormous portions of Alaska, sometimes at depths measured in hundreds of feet. For decades, builders treated it like solid ground because for a while, it behaves like solid ground. Conventional concrete foundations were poured on top of it. Posts were set into it. Heavy log structures were built on it. And for a year or 5 years, or sometimes even a decade, everything looked fine. Then the permafrost shifted, or thawed slightly around the heat source of the building above it. One corner dropped. A wall cracked. The door frame racked, and the door stopped closing. The logs shifted. The chinking fell out, and the cold began pouring in through gaps that were not there the season before. Traditional cabins in Alaska are not just fighting the weather above ground. They are fighting the ground itself from below. And that fight, unlike the weather, does not give you any warning before it starts. A Quonset hut changes the equation in two critical ways. First, it is dramatically lighter than a log structure. A traditional log cabin carries tens of thousands of pounds in structure alone before you add contents, snow load, or equipment. A steel Quonset arch system, for a similarly sized structure, weighs a fraction of that. Less weight means less pressure on the permafrost beneath it. Less pressure means less deformation, less thaw, less movement. The structure simply does not push down on the ground the way a log cabin does. Second, the foundation options for a Quonset are inherently flexible. Helical piers, essentially giant steel screws driven into ground, can be adjusted as the ground beneath them shifts. A properly designed Quonset on helical piers can accommodate ground movement that would destroy a conventional poured foundation. You can go back and relevel the structure without rebuilding from scratch. That is not possible with a traditional cabin on a conventional foundation. Once that foundation moves, you're either living crooked or you're starting over. The combination of low structural weight and flexible, adjustable foundation options makes the Quonset one of the most permafrost-compatible residential structures ever designed. The men who understand this are not switching because a Quonset is cheaper. They are switching because they did the research and realized they have been fighting a problem that did not need to exist. One of the most persistent myths about building in Alaska is that quality construction requires specialists, time, and money in quantities that put it out of reach for anyone who is not a contractor or independently wealthy. A traditional Alaskan log cabin, properly built, properly chinked, properly insulated, runs somewhere around $200 per square foot in most remote areas of the state, when you factor in labor, materials, and logistics. In remote locations where everything has to be flown in or barged, that number climbs higher. It costs less than the boring rectangular box it replaces. It performs better in every measurable way, and it looks more interesting. The aesthetic objection dissolves the moment someone actually walks into a finished Quonset interior. The men who have built them know this. The men who have not built them are still carrying a mental image from 1944. The aesthetic wins are real, but so are the practical challenges, and glossing over them would be dishonest. Curved walls mean standard rectangular furniture sits away from a wall on the lower sides of the arch. That is a real consideration. The solution is straightforward. Keep primary furniture pieces central in the space. Use floating shelves that follow the curve of the arch rather than fighting it. Or, as many experienced Quonset builders do, frame a partial straight interior wall on the lower sides of the arch, giving yourself a flat surface for cabinets, shelving, and built-in storage while preserving the dramatic open curve overhead at the center. Done well, that detail becomes a design feature rather than a workaround. Condensation is the other issue that requires proper attention. Metal conducts cold. If your spray foam insulation is not continuous, not properly applied, not the correct thickness for your climate zone, you will get condensation on the interior steel surface. That condensation is not cosmetic. Left unaddressed, it leads to rust, moisture damage, and interior air quality problems. The solution is not complicated, but it is not negotiable. Close cell foam at full recommended thickness, a minimum of 2 to 3 inches in standard Alaskan conditions, and more in extreme cold zones, applied continuously without gaps or thin spots. Get the insulation right, and condensation is not an issue. Cut corners on the insulation, and you will pay for it slowly and expensively over time. Acoustics are a legitimate concern on an uninsulated metal shell. Rain or hail on bare steel is loud. Once spray foam is applied and an interior finish layer is added, whether pine paneling, drywall, or rigid board, acoustic performance improves significantly. Most Quonset owners report that after proper finishing, the interior is quieter than they expected given the material. Permitting requires homework, depending on your location. In remote Alaska, many areas have minimal or no permit requirements for residential structures under a certain square footage. In organized boroughs, local codes need to be checked, not because Quonsets fail structure requirements, but because some zoning codes were written when the only residential buildings anyone imagined were rectangular. That is changing as off-grid and remote living grows. But verify before you break ground. There is no press release about what is happening across Alaska right now. No announcement. No trend piece in a national publication. It is quieter than that. It is one build at a time, on lots that most people will never drive past, among men who did their research, ran their numbers, and decided that fighting the same losing battle with the same structure every single winter was no longer worth it. These are not men who gave up on quality. They are not men who settle for something cheaper because they could not afford better. They are men who questioned an assumption that had gone unquestioned for generations and found that the assumption was wrong. The traditional cabin is not the only answer. It is not even the best answer. It is simply the answer that became habit. The men who have made the switch are sleeping through blizzards that used to keep them up managing a dying fire at 3 a.m. They are cutting their heating bills by half and spending that money on something other than propane. They are building on ground that would have shifted and cracked a conventional foundation within a decade, and their structures are staying level and tight. They are doing all of it faster, cheaper, and with more confidence than the men still swinging hammers at conventional log walls and wondering why the same problems keep coming back every spring. This is not a fringe movement. It is a quiet, practical reckoning, and it is spreading one man at a time across the state. Come back to the image that started this. The old log cabin, buried in the blizzard, snow stacked on the roof, visible through the enormous arched window of the structure looking out at it. That cabin is not backdrop. It is not scenery. It is a before picture. Everything that cabin represents, the ice dams, the heat loss, the permafrost pressure, the structural load, the 3 a.m. fire management, the propane bills, the annual damage cycle, is sitting right there in plain sight through that window. The Quonset looking out at it is the after. The arch sheds a snow load passively, without you climbing onto the roof in a storm. The steel holds under compression loads that would collapse conventional framing. The spray foam locks the heat inside continuously, from the base of one wall to the peak and back down the other side, with no gaps, no cold bridges, no settling over time. The helical piers move with the ground beneath them instead of cracking and shifting against it. And the man inside is warm. His dog is warm. The storm doing its absolute worst outside is doing nothing to them. Nothing at all. That is not luck. That is not circumstance. That is engineering. That is geometry. That is what happens when you stop building the way people have always built in Alaska, just because that is how people have always built in Alaska, and you start asking whether there is a better answer. There is. It has been sitting in plain sight since 1941. The smartest men in the state are finally paying attention, and the results are showing up in their heating bills, in their sleep, in the structures still standing straight and tight on ground that swallowed their neighbors' foundations years ago. This channel is for the men who ask better questions. If that is you, hit subscribe, because this is exactly the kind of conversation we keep coming back to. Are you still in a traditional cabin? Or have you already made the switch? Drop it in the comments below.